so we can start.
Okay.
All right.
Good evening, everyone. Welcome to another session of the networks. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems, ISC. Today's talk is by Professor Chetna Singhal, and she will be speaking on evolution and future of multimedia services in wireless networks. Dr. Chetna Singhal received BE in Electronics and Telecommunications from the University of Pune, India in 2008, MTech degree in Computer Technology from the Indian Institute of Technology, Delhi in 2010, and PhD degree from IIT Delhi in 2015. She worked in IBM Software Lab, New Delhi as a software engineer in 2010 for a year. She is currently an assistant professor with the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur, since 2015, and IEEE senior member since 2021. She received Pune University Gold Medal, IIT Delhi Academic Excellence Award, and DST Inspire Faculty Fellowships in 2008, 2010, and 2015, respectively. Her research interests are in next generation heterogeneous wireless networks, UAV networks with emphasis on cross-layer optimization, adaptive multimedia services, energy efficiency, and resource allocation. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Singhal towards the end of the talk or type them in the chat box and we'll moderate it with her. Over to you, Professor.
Thank you so much, Soumya, and good afternoon to all. Really nice that I'm getting to interact with all of you and to be able to present some discussions on multimedia services in wireless networks. So evolution and future of multimedia services in wireless networks comes from the prevalence and excessive usage of multimedia content in our daily life, which are characterized under the groups of multimedia services. And the wireless network standards are also getting evolved, and the standardization efforts are looking at how to enhance these multimedia services and the new requirements that are coming with newer applications on a daily basis. So before we get into what the wireless network standards, the next generation networks can support in terms of multimedia services, it is important to firstly understand what is multimedia, right? So multimedia is basically an interactive representation of information using multiple forms of media types. Individual media types include your speech, audio, text, image, video, graphics, as well as animation. So this information comes from the real world, as well as the synthetic information can be embedded into the multimedia content. And we can see through the subsequent discussions, we will see how the multimedia standards have come up to integrate these different media types and the various applications that have come up because of it. Talking more about multimedia, so your audio and video constitutes the continuous media, which is varying. So this part of the information is varying with respect to time. Whereas there is another part which is static in nature, that is your image and text, which does not vary as such with time. It is more static in nature, but overall in a multimedia file, there would be synchronization between the continuous as well as the static media type. And we use multimedia content in our day-to-day activity. Over the internet, we use applications like video telephony. Voice inherently would be associated with other media types like video, along with the voice content exchange between two participants. Then even video on demand characterizes as a multimedia application. And when we are using smart devices at home or in office, such as in applications like navigation systems, interactive television, again, we are dealing with some form of multimedia content. So multimedia is used everywhere in telecommunications, consumer electronics, TV production, publishing houses, etc. Various examples of multimedia applications are listed here. So we are not limited just for the entertainment purpose. We are consuming the multimedia content. We are using that even in science and technology, in education, medicine, information kiosks, web applications, simulation, and virtual reality. And in this presentation also, it's with the help of the network, along with the applications that we are using, the video and the audio is getting captured at my end and it's being relayed to everyone out there. Right. So this also characterizes as a multimedia service and a multimedia system. So there are several challenges associated with multimedia services. So some of these challenges are listed here. So there is too much of information that has to be processed, and we'll understand with the help of examples why am I saying that it is too much information. Compilation time is high, computationally and monetarily it is expensive. And why is that so? If you understand, at your end you must be using a smart device, and same goes at my place as well. I'm using my laptop, and maybe some of you are using computers, desktops, or maybe a mobile phone. So at both ends, we are using some kind of a processing unit, which is actually capturing and then thereafter packetizing the information and sending it over the network. So definitely a lot of computation goes in all these processes. Furthermore, the resources and processing requirements are also many when we are dealing with multimedia services. And synchronization also is an important part of the process when multimedia content is being used. Overall, whenever we deal with multimedia information, so specific media types can be characterized further into some information units, which are known as the logical data units. The definition of a logical data unit differs when we move from the domain of audio content to video content. And similarly, when we move towards the synthetic information also, the definition of LDU could change. And why am I introducing this here is so that we understand that whenever we are dealing with multimedia systems at the application layer, whenever we integrate it to the network and we are sending the multimedia information over the network, there is some kind of a mapping that needs to take place, and it is based on context. So if, for instance, you happen to work at the physical layer, for the engineer working at the physical layer, perhaps the channel condition and the signal design and the way the signal is sent and received becomes more relevant. Whereas somebody who's working at a higher layer, maybe the bit at the bit level, how the encoding process happens and how the bit stream is created, that becomes more relevant. And furthermore, if we move higher in terms of our layers in the network, we would be dealing with packets, and thereafter, if we go to up to the application layer, we would be dealing with the application layer information, right? So when we are dealing with the application layer information for a video, we can characterize the video and study it at any one of these levels. So at the lowest level for a video, we are dealing with the pixels that are the smallest unit of information inside the visual content, right? So if we were to deal with the images also, pixel would be the smallest unit of information, which actually stores the color as well as the intensity information spatially, right? Then these pixels combinedly create blocks. And whenever we are dealing with videos or images, there is a block level processing that is performed. So these pixels are taken together to form blocks, and blocks together form frames, and these frames together will be grouped together to form group of pictures, or in this example, it is clips. And several such clips will be combinedly forming a film. So we can understand the granularity at any of these levels, and depending upon what is the context at which we are trying to study the system or design the system, the definition of a logical data unit would change. And whenever we are dealing with streaming of information, the mapping of LDU can happen onto the protocol data unit, that is the PDU. If we compare the traditional data and multimedia communication, there are certain parameters based on which we can distinguish between the two. So, for instance, data communication is a very generic term wherein even at low data rates, the data communication can be supported. But when we deal with multimedia communication specifically, to support the QoS requirements or to maintain the quality at a reasonably acceptable level, we need high data rates. The data communication traffic would be bursty in nature, whereas multimedia communication, it would be stream oriented or highly bursty. When we deal with high bandwidth communication channels, in that case, we could have multiplex multimedia information coming from multiple sources, and the nature of the traffic would be bursty in multimedia communication as well. In terms of QoS requirement, for data communication, the QoS requirement can be classified as low best effort, whereas for multimedia communication, it has to be guaranteed. And in terms of transmission connectivity, point-to-point data communication applications are more prevalent, whereas for multimedia communication applications, there are two types of use cases, that is point-to-point as well as point-to-multipoint. Latency requirements for data communication may be undefined, and for multimedia communication, definitely for an interactive service, you would require predefined latency requirements. So for instance, if we talk about VoIP application, we need a 150 millisecond latency that has to be met. So this is the upper limit on latency. Anything less than this is acceptable. In terms of reliability requirement for data communication, for applications such as file transfer, it cannot accept any kind of losses. Whereas for multimedia communication, the information is relevant based on time. So this can tolerate some losses. So for instance, right now this session is being streamed. So in case your network goes bad, some of the packets might get dropped and the quality might vary of the session. But nevertheless, if the network comes up again in, let's say, a few seconds, still the session would be tolerable at your end. Whereas if I was sending on the contrary, if I was sending a file, let's say over FTP, if the network goes bad, then the file transfer could get corrupted, and at your end, you would be not able to use that file. So that is where this reliability requirement is very different than the traditional data communication for this multimedia communication case. Then for the mode of communication, data communication can be asynchronous. For multimedia communication, it has to be synchronized. And type of traffic, when we talk about data communication, we are dealing with data which is a very generic term, and it classifies as a single traffic type. We are not distinguishing between the types of data here. For multimedia communication, there can be multiple traffic types, and traffic classes can be defined based upon the application. So for instance, VoIP is delay sensitive. So definitely your resources or scheduling should cater to the resource allocation for such a delay sensitive application before it gets allocated to something which can tolerate delay. A very simple example of a multimedia system has been shown here. So this entirely can be classified as a multimedia system. A part of it can also be classified as a multimedia system, depending upon what we are considering in a given use case, right? So for instance, if I remove this part of this diagram, still it classifies as a multimedia network, just these devices connected over LAN, wherein some audio video content is captured and it is being relayed to the local viewers. If we connect the internet these remote viewers over the internet to this system, that also classifies as a larger multimedia system. So if we talk about the specific components of multimedia content, so to understand how the evolution has happened, we need to understand how the standardization efforts and the various popular methodologies have been adopted for individual media types. So starting with audio and speech, we'll go on to discuss about the video codecs. And thereafter, we will see in the next generation wireless network standards how these are actually becoming relevant for various applications. So starting with audio coding, so we all know that the audio information is basically in a 1D signal which is varying with respect to time. So for the audio, what we capture is our sound pressure level in dB, which if we have to encode and convert into a digitized format, the steps followed are as shown here. So we need to do sampling, then quantization, then encoding needs to be done. Now the encoding can be based on the various compression algorithms that are there available. The simplest one being the entropy coding. So in an entropy coding, we can use either Huffman coding or arithmetic coding to compress the quantized samples, right? And apart from this, we have differential coding, then we have parametric coding and subband coding. So each one of them results in different level of compression that can be achieved in this particular block. Okay, but the overall objective of this coding is to get this binary pattern. So this bit stream, so the audio information can, through this, these set of steps can be converted into the bit sequence, which can then be transmitted over a network by using certain protocols. And the most popular term that you all must have come across is this codec. Codec is basically dealing with coding and decoding, and also inherently it is performing some form of compression and decompression. And we all should understand, while performing these steps, there is some amount of information that gets lost, and that is because of this quantization step. Okay, and why do we perform quantization? Because our systems are cannot handle infinite number of sample amplitude, so sample values, right? So this up till this level, if we look at the number of values that xn can take, it would be infinite. But after quantization, we limit the number of values that can then be coded using a specified number of bits. Okay. Now the sampling operation also depends upon what type of audio input are we dealing with. So in order to understand what are the sampling rates, we should know what are the different types of audio information that is relevant to us. So if we talk about human speech is limited maximum up to around 4 kilohertz. So it is definitely lesser than 4 kilohertz, but that is the upper limit that is considered in systems. So sampling rate for speech signal is considered to be 8 kilosamples per second. If we are dealing with audio content, which is generic in nature, which also has music in the background, then in those cases, we would have a higher sampling rate. So the audible frequency range for humans is from 20 hertz to 20 kilohertz. So definitely your sampling rate dealing with a generic audio input would be up to 40 kilohertz or more. So there is a CD audio format which has a sampling rate of about 44.1 kilosamples per second. So depending upon the type of audio input, we would decide our sampling frequency. And also these parametric coding and subband coding are also taking into consideration that ultimately this audio information will be used by users, that is humans. And accordingly, these parametric models can be used, and some psychoacoustic study-based inferences can be used for subband coding. So I'm not going into the details of all this, but I'm just giving you some background information on audio coding here. Then thereafter, if we look at the various standards and various formats for audio content, The most popular one being MP3. So even in today's date, we are using the MP3 audio format. So how did it get, how did we reach up till the MP3? What was the evolution that took place here? So if we talk about the MPEG-1 audio, it is audio which is considering a data rate from 64 kilobits per second to 320 kilobits per second. And the uncompressed CD audio, if we take, it is 1.4 megabits per second. How did we get this value? We got this value by considering firstly the sampling rate and thereafter number of bits assigned to each sample. Okay, based on that, we have got this value. So the compression factor from here to this particular bit rate is about 2.7 to 24. Okay, and correspondingly, the compression rate has been mentioned here. And there is a support for two audio channels. So monophonic means there is a single audio channel. Dual monophonic means two independent channels. Stereo is two channels, and joint stereo would take advantage of correlation between the two channels. Then we have the MPEG-2 audio coding, wherein we have a support for multi-channel. Then there are other variants for MPEG-2 audio, which is mentioned here, like low sampling frequency support, then advanced audio coding for MPEG-2, which supports 7.1 channels. And this inherently would have more complex coding. And there is definitely, whenever a new standard is introduced, then there would be backward compatibility with the previous decoders as well. Then we have the MPEG-4 audio coding. So MPEG-4 audio consists of 3 layers, and the MP3 that we talk about is the layer 3 in MPEG audio. Okay, so this MPEG-4 audio consists of natural coding and synthetic coding, and synthetic coding is more relevant when we are dealing with applications that use text-to-speech synthesizers, and also when structured audio is used. So what is structured audio? Basically, if we see in today's date, the music is not just generated using the musical instrument. Synthetic music can also be generated. So there is this MIDI, which is your musical instrument digital interface, which can help in generating the music content and also in digitizing it. Okay, and here we take the event list and the parameters, which can enable generating the same musical sound at the time of playback. Okay, so the structured audio has several applications, including the low bandwidth transmission, then sound generation using the process models for music applications, for content-based retrieval, and for virtual reality, together with the VRML, that is the modeling language, and the real-time 3D. And what can we expect in the future? So currently there are a lot of efforts being made towards this hypersound technology, which is dealing with the directional audio. So what is happening here is that using high frequency sound waves, using an array of electrical devices called piezoelectric transducers, it is possible to create directional audio. So generally, if we look at the frequency band for the audio signals, limited up to 20 kilohertz, these frequency signals would spread as they move away from the source of the sound. Whereas by using some phenomena wherein higher frequency waves are used, and by the process of cancellation of these signals, the resulting signal would be in the audible frequency range, and so the spread of these signals would be very limited. So the spread out will not happen. So these higher frequency waves have shorter wavelength and they diffract less as they travel. So the applications for this directional audio would be in crowd control, commercial advertising, train signaling devices, and for long range acoustic devices, which can be mounted on ships for sending warning to other vessels. So this is the future of audio, wherein you can have advertising through some digital boards, wherein a user who's present in front of the board will only be able to hear the sound related to that advertisement, rather than every passerby, right? So this might be the future that we get to see in the domain of audio. Then talking about the video standards and why is video so important? Definitely audio is important, but audio contributes to a very small amount of data inside the multimedia information, right? The maximum amount of data is coming from the visual information that is in the form of video, right? So we have different video standards and each of them deal with different resolutions. So all of us are using HD devices these days. Smartphones are being advertised with the resolution formats that they can support. If you walk into any Chroma center or any such electronic appliance showroom, you will find that the television screens are being advertised with ultra high definition resolutions and 4K resolutions. So all of these resolutions actually are talking about this luminance and the chrominance resolution. So luminance part is your grayscale intensity, you can understand, and chrominance resolution or this chrominance component is dealing with the color information, right? And there are certain steps that are followed, such as your color subsampling, the frame rate is important, aspect ratio is important, and whether interlacing is supported or not, that is also important. Now, what is this interlacing is, so whenever we scan a video frame, so the scan happens row wise, right? So when the evolution was taking place from the earlier days television screen, the frame rates would have been very less. So the updates in the video signal on the screen was slower. So to counter the flickering update of video on the screen, the interlace scanning was proposed, wherein alternate rows were scanned and updated separately. Okay, so that is what your interlace scanning is. So I'm not getting into this interlacing concept here, but in case somebody wants to know more about it, definitely you can ask me later, right? What is important is how this evolution has happened and where we stand in today's date. Okay, so this slide is basically giving us the different resolutions and different resolution formats that are supported in various applications. Okay, and where we stand in today's date is this HDTV. So if you happen to see television content, the maximum resolution that is supported right now is HD. Definitely higher resolutions are there in your other video information, but definitely the TV broadcast is not dealing with a higher resolution than HD currently. But what is the future? In the future, we will be dealing with very high resolution, as high as 4K and 8K. So these are your ultra high definition resolutions. And here you can see the resolution deals with these many number of pixels across a row as well as a column. So how many number of pixels do we have here? It would be around 33.2 megapixels of information. And let's assume that we are using a true color format. That means we are assigning 24 bits per pixel. So the amount of data that we are dealing with is in several GBs, right? And let's say you want to stream this information. So when we stream this information, this resolution is dealing with only one frame, right? And a video constitutes several frames that are defined in terms of your frame rate, that is frames per second. So if you compute overall the amount of amount of data rate that is required to stream the uncompressed video, it would be in several GBs per second, which is very unrealistic, because the networks don't just support one single video at a time, they have to support several such streaming sessions at one instance, right? So definitely we cannot deal with the uncompressed video as it is. So this is just a comparison of your screen resolution. Right now we are dealing with up to full HD in many of the devices. Some of the TV screens and displays have started supporting higher resolutions, but still it is yet to become more common. So this example here tells us why compression of a video is important and why these video compression standards have evolved to support higher resolution. So if we deal with, let's say, a 1080 cross 1920 resolution video, then for a 60 frames per second frame rate, it would contribute to 3 Gbps data rate requirement, right? And as you can see, this is not even 4K or 8K resolution. And this is a very unrealistic expectation from the network to support a single uncompressed video streaming, right? Similarly, for this resolution also, the requirement is several hundreds of megabits per second, which is unrealistic. So what are the steps that are followed to reduce this data rate requirement? The first very prevalent step is your chroma subsampling. So we as humans are more sensitive to the intensity variations as compared to the color information variation. So that is why we can simply drop some of the chrominance components, which is carrying your color information, and we straight away go for these chroma subsampling formats. So if you happen to open your TV screen or any display settings, right, and if you read the settings as well as the specifications, you will definitely come across something like this, right? So here what it means is all the luminance components are retained as it is, and some of the chrominance components are dropped. So generally, whenever we are representing our video information, we don't use the primary colors. That is, your RGB are not used to store the color information. Instead, to have a backward compatibility with the black and white screens which we had in earlier days, what was done is whenever the color TV content was to be sent, they started sending the grayscale information in the form of the luminance information, that is your luma component, and the color was reduced to the two chroma components, which could either be CRCB, or you have different formats like YUV, where U and V are the chrominance components. So we can drop some of them, the color information, amongst the neighboring pixels, and we can still reconstruct or display the video back with a reasonably acceptable quality, right? So this straightforwardly reduces some data rate requirements, right? Furthermore, there is a lot of redundancy in your video information, right? So there is redundancy in terms of the spatial information, that is your spatially co-located pixels will have intensity which would be very similar, right? For instance, if you look at any scene coming from a real world, there would be some background and there would be some foreground object. Background would be, if it is of a common color, all the pixels in that background might be of the same color. So definitely, spatially speaking, you don't need to store and encode every pixel individually. You can just remove the spatial redundancy by performing the intra-frame coding. And similarly, temporal redundancy can also be removed. Now, what is this temporal redundancy? It is based on the high frame rates that we are dealing with. So for example, if I see this 30 frames per second video, this means that every frame has to be displayed for 33 milliseconds. Now, for 33 milliseconds, within that much time, amount of time, generally the real world scenes would not change much, right? So a lot of the portions of your video frame will still remain the same from one frame to the next, right? So this redundancy can be removed by performing the inter-frame coding. And we do not deal with the intensity values of the pixels originally from the original frame. Rather than that, we move to the transform domain by using a very popular transform, that is your DCT, discrete cosine transform. Now this is used both, was used both for your image compression in your JPEG standard, and this made way to your MPEG standard for your video compression as well. So basically what we do is, when I earlier mentioned about block-based coding, what I meant was that the entire video frame is firstly broken down into smaller blocks. right? Now the block could be of this size. Now this block is transformed by using the two-dimensional or 2D DCT, and what we get after that is the transform coefficients. Now these transform coefficients will be equal in number as the input number of pixels inside the block. Okay, then after that the quantization can be performed to give us the quantized coefficients, which are then encoded and sent across over the network or stored. Now, what is the relevance of this transform? We'll understand through this diagram. So if you look at the DCT coefficients, after performing this transform function, you would have a DC component here, and the low frequency information would be in these coefficients, medium frequency would be here, and high frequency would be here. So if we only retain some of these components and we drop the high frequency coefficients, still the reconstructed content would be of reasonably high quality. And this has been extensively studied, that to what extent can we quantize these coefficients. Based on that, we can either have a quantization matrix that is used in encoding standards like JPEG, or we can decide a fixed quantization level as is used in your video coding based on how much of these coefficients do we want to retain. Okay, so here if we understand logically what these mean, so the vertical edges would correspond to some of the coefficients here, horizontal edges would correspond to some coefficients here, and high frequency variations in intensity levels in a block would correspond to the coefficients here, which can easily be dropped to retain the equivalent amount of quality, visually speaking. And these are the equations for your 2D DCT. The best advantage of DCT is that you can simply apply this in the form of a matrix operation. Okay, so there can be a transform matrix which can be applied twice to the input block. And since the block sizes are limited to 8x8 usually in several video coding standards, so it becomes an easy process to follow. So let us then discuss about how the evolution of the video coding standards happened, right? So starting from H.261, which was introduced several decades ago. So this was introduced around 1988 to 1990. This was specifically designed for video conferencing and video telephone applications over ISDN telephone lines. Now you have to understand that the standardization efforts are made based on the requirements from the various applications at any given point of time. And at that point of time, these applications were very popular. Okay, and the network was implemented using this ISDN framework, and because of which the standard itself was limiting the bit rate after performing the compression, which would easily get mapped to the channels of ISDN, right? So here the bit rate target was a multiple of 64 kbps, and this multiple P could be in the range of 1 to 30. Okay, and it supported subsampling of the format 4:2:0 and very low resolution. So you can understand at that point of time, 1988 to 1990, the devices themselves were supporting very low resolution. And for video conferencing, video telephony kind of applications, the corresponding resolutions reflected in the standard as well. And this standard later on had a lot of influence on H.263 as well as MPEG 1 to 4. And this is the different type of frames after encoding we get in H.261, which is your I frame and P frame. I frame is intra frame, P frame is your inter-predicted frame. In intra frame, we are only removing the spatial redundancy. In P frame, we are removing the temporal redundancy as well. And there is an important term macro block which is used up till the H.264 standard. Thereafter, we use different terms in the latest standards like HEVC and VVC. I'll come to that subsequently. So this is the set of steps that are followed for intra-frame coding. And these are the set of steps followed for inter-frame coding. I'm not getting into the details of this because we have limited amount of time and there are many other interesting things I would like to discuss. So if we see, the various standards have come about over the decades. So right now, if you see, the most popular standard, which was introduced more than a decade ago, more than, I would say, 15 years ago, this ASA 264 ABC standard is still being used, right? And we are slowly and gradually moving towards the HEVC standard. So HEVC got introduced around 2013, and it got, the standardization efforts kind of still evolved after 2013. There were different variants that were introduced in 2015, and so on. And in today's date, where we stand is this versatile video coding. Okay, and all these standardization efforts are performed by these groups that come together based on the requirements at that given point of time, decide which methods should be included inside the standard for the design of encoders, such that independent decoders will be able to decode the information. Okay, so this is where we stand in today's date. So if we look at the timeline, so H.264 MPEG AVC stands for your Advanced Video Coding format. This was standardized in 2003, but it still continued to be used. So HEVC got introduced around 2013, standardized in 2013. It supports ultra high definition resolution, and it is more efficient than your H.264 or MPEG-4 AVC. Then today where we stand is this VVC, that is also known as your H.266 or versatile video coding, which has a 50% higher coding efficiency than your HEVC standard. And this has been designed, or it is being introduced because we need a support for very high resolution, that is your 8K resolution. So there are several differences between H.264 and H.265. I'm not getting into the details here, and also the encoder as well as decoder. But definitely whatever I have discussed so far, that is your spatial redundancy removal, your temporal redundancy removal, that finds way inside the encoder and the decoder for both HEVC as well as for VVC. And what we see over the years is, and with the evolution of these video coding standards, is that we are actually increasing the coding block size from AVC, which supported a 16x16 coding block size. And this coding block block was defined in the form of a macro block, right? In HEVC, it became not a macro block, but a CTU, that is a coding tree unit. And in VVC also, we call it a coding tree unit, but the size of that block, that is the coding block, is increased to 128 cross 128. Similarly, your transform block size is also increased, from 8 cross 8 to 64 cross 64. So what is the advantage of using bigger blocks? It improves the compression, but there is a trade-off. There are blocking artifacts, because bigger the block, so independently, if you are encoding them, what would happen is that the neighboring blocks would have different intensity patterns, and there would be a visual distortion that can be apparent to the viewer, right? And there are ways to reduce this blocking artifact by using filtering processes. So I'm not going into the details of that, but whoever is interested can definitely look at these references on VVC, which have just come up in the recent years. Okay, so here these set of plots is actually from this reference is showing how, in terms of bitrate, the VVC encoder reduces the bitrate requirement as compared to the HEVC. Okay, and there are different encoder formats that have been used in the study to gauge what is the bitrate reduction achieved and how fast the computations can be performed by each. There are several extensions to these video coding formats and standards. So we have extensions like scalable video coding. So SCC is for H.264, SHEVC, sorry, this is not E. SHVC is for HEVC, the scalable video coding extension for HEVC. Then we have support for multi-view coding and 360-degree video coding. So this actually falls under the category of multi-view coding. So we have an extension both in H.264 as well as HEVC for multi-view content. Now, where do we see VVC being used? What are the applications of this new video coding standard that is coming up? So it can be used for computer generated or screen content, as occurs especially in computer screen sharing and gaming. It will be relevant for immersive and augmented reality applications, as well as applications requiring ultra low delays, such as wireless displays and online gaming. And if you are following the way wireless network standards are getting evolved, you would understand the requirement for ultra low delay for certain scenarios. Okay, so definitely in the video coding standard also, that needs to get reflected, and that is what is being targeted in this particular standard. Right. Now, we need to see also from the perspective of our wireless network standards, what is happening out there, right? So we all hear about 5G coming up, right? And already in the research phase, 6G is being talked about. So how does this evolution happen, and where does these multimedia services, fall in this entire development, right? So definitely you can go to the CGPP website, and there you will find the various releases that are projected and which are frozen. So the latest release, which is already finalized, is the release 17. And if you look at the release 17, the various work items and the various study items that are highlighted here are dealing with multimedia services. So whether it be 5G multicast broadcast, whether it be NRQoE or advanced interactive services, and within the unmanned aerial systems also, there is a support for multimedia services that we'll see through the slides hereafter, and also multimedia priority services. So what we will discuss from out of all these will be the 5G multicast broadcast and the new radio QoE, and within the unmanned aerial systems, what are the multimedia support services that are supported. Okay, and also within the release 18, which is the projected set of work items that the various researchers and the industries are actually targeting, are listed here. So there we can see from the CGBP website itself that there is a target to support these extended reality and media services. Then there's the further enhancement for your 5G multicast broadcast services is going on. It is in the phase 2. Then within this, you can see for the multimedia codecs system and services, there are different sub-points which are mentioned here. So if you happen to look into this document, and if you look at how the evolution is happening, you will find details related to each one of this, whether it be the architecture, whether it be the codec support, what are the video codecs that 5G services will support, and how the artificial intelligence and machine learning can enhance these services, and various other extensions are mentioned here, right? So because the time is limited, I cannot explain or discuss each one of this, but nevertheless, through this presentation, I'm just introducing some of you might already be knowing about it, but some of you might find this interesting actually, to explore how the technology is getting developed and how the standardization efforts are including the newer use cases and applications. And also here we can see the QoE enhancement. Now this word QoE might be new to some of you. Many of you might already be knowing this. QoE deals with your quality of experience. Oftentimes when we are dealing with networks, we deal with the lower layer quality of service, right? Whereas when we talk about the application layer, and specifically for multimedia services, we are dealing with the application layer. There, the same notion of QoS may not be applicable. So what we need to look at is the quality of experience instead of quality of service. So if I talk about 5G multicast broadcast, which is most relevant for your mobile television application, so there are certain definitions that have come about after release 11. So in release 14, SEMBMS got introduced. This was specifically for your LTE and LTE advanced. And here they provided a provision to allocate the entire transmission capacity for your broadcasting services. before this release, there were some upper limits that were defined because your unicast services were also to be supported along with the broadcast services. But hereafter, after this release, the latest release gives that freedom to a network service provider to use the entire set of radio resources for the broadcasting services itself. So what do we expect in the future? In the future, this technology could be integrated into smartphones, tablets, and televisions, wherein we could just simply receive the TV broadcast content on our mobile phones. So we have to understand how is it different to the way we are receiving the content in today's days. We still have these applications wherein we are receiving, live television content, but we have to understand that that is happening on a one-to-one basis. So let's say I, as a user, log into an application and I'm receiving that content. I might be getting that content, although it is termed as a television, live TV, or let's say TV content, but maybe it is in the background using the resources on a one-to-one basis, wherein I am getting that content. Maybe others might not be using the same set of radio resource to get their content. So that is the traditional difference between your multimedia broadcast and video on demand also. Okay, so here I'm just showing a diagram of an architecture, how an adaptive or an efficient multimedia broadcast can be supported. Because the time is limited, I would not go into the details of this. Rather, I would discuss about how the evolution from 4G LTE to 5G NR and 5G core for multimedia broadcast services has happened. So we see that up till release 16, we were still dealing with 4G LTE, but for 5G NR, 5G core, we are now dealing with release 17, which have introduced certain changes in the network architecture, in the physical layer, service continuity, in the RAN protocol to support the new radio multimedia broadcast and multicast services. Okay, and with respect to this, you can again see the release 17 document to know specifically what are these changes within each of these points mentioned here. Next is your QoE. So I was mentioning about quality of experience, which is very, very important. Now, what is there in 5G is that the QoE will be shared and it would be visible to your radio access network. And this is a very, very important point because your efficient streaming or efficient transmission can happen if your radio access network has information about the QoE. That is the quality that a user is actually experiencing while receiving the multimedia content. So QoE is an application layer measurement which is configured by the OAM, that is your operations, administration, and maintenance. And in the 5G architecture, this will be visible to your radio access network. So you can find further details of this inside this document. The document number is mentioned here. And to enable measuring the impact of the mobility on application and users QoE, it is required to support QoE measurement, reporting, continuity in intra-system, radio access technology, intra-rack, intra-node, and inter-node mobility scenarios. And this is being this was targeted in release 17 and it is expected to be there in the future 6G standard as well, and in the future releases as well. Next is in the unmanned aerial system. If we look at the services that will be supported. So this again table has been picked up from the CTPP release document, release 17 document. So we can see based on the type of service, the end-to-end latency has been specified. And let's say for 8K live video live broadcast, the latency requirement over 100 Mbps UAV originated video is 200 milliseconds. But for 600 kbps UAV terminated, that is when the video is being received by the UAV, a lower latency has been defined. So for different areas and for different services, different latency requirements are mentioned here. But definitely the future wireless network standards are actually integrating and considering the multimedia information and multimedia services inherent to all kind of use cases and scenarios. Okay, and so we can see here that even in unmanned aerial systems, there is a discussion about supporting the multimedia services. Then also another important thing that is coming up in the future multimedia services is your 360-degree video, which is also known as your immersive multimedia service, or there to have more efficient streaming supported. So there would be a requirement for adaptive multi-view 3D video coding such that the heterogeneous users can be supported. And this here in these set of slides, I was trying to actually give one such example, how the adaptive encoding can enable the rate requirements coming from your dynamic network conditions. And this work was done by one of the students who was working with me. So the student actually worked with this HTM 16.3 software and encoded the HEVC content for your 360-degree video at different rates and studied how the PSNR performance is there when different target bit rates are achieved. Okay, so I'll not get into the details of these results for now because just a few more minutes are there. Rather, I'll talk about something else, which is kind of the future also, I would say. That is your immersive multimedia applications. And this is also reflected in your release 17 and release 18 documents, right? So what is this immersive multimedia? So basically for immersive multimedia, there is a frame of reference and the content is captured all along the frame of reference. So the viewer would either be using a head-mounted display or the content can also be seen on a mobile phone. So if, for instance, you open YouTube and you search for a 360-degree video, you will find many such videos are already uploaded there and available online, right? By just changing the direction of your mobile phone, you can change the viewing angle and see the revised content on your screen, right? But this is not just limited to how the playback happens, but the main challenge is how it is captured, stored, and streamed. Because when we talk about wireless networks would have dynamic channel conditions, and definitely your 360-degree video cannot be streamed as it is, because we all know that at any given point of time, a human would be seeing in a particular direction only. So we can have adaptive methods to send the content in the visual direction. So in the field of view, wherever the viewer is watching, the viewport generally what we do is we split this entire 360-degree video into smaller tiles or smaller regions known as tiles, and we can send that respective tile which is being seen by the viewer at any given point of time at a higher quality as compared to the remaining tiles which are not being seen at that point of time, right? So there are several technical solutions and several research frameworks which have come up in this area, which in case you are interested, you can definitely explore. But this is just giving you some insight into what is expected in the future. And both in terms of your video coding standards and in terms of your wireless network standards, there is a support for the 360-degree videos. Okay, so this was just some solution which one of the students working with me had come up with, wherein again a high PSNR with a low bit rate was targeted by considering tile-based streaming of this 360-degree video. So I'm not getting into the details of this solution, but nevertheless, what is expected in the future is these set of applications as well. So virtual reality and augmented reality, wherein we are integrating both the information from the real world that might have been captured beforehand and the synthetic information that is being embedded into the pre-recorded information, as well as a lot of effort is going on 6G, which will be inherently making use of artificial intelligence for several use cases and work items, not just limited to multimedia services, but also how the resource allocation will be happening, how the other aspects will also look into using this machine learning and artificial intelligence tools to have more efficient solutions. So these are some of the references. So if you have any questions, comments, or remarks, I welcome them. Otherwise, you can always send me an email on this email ID. And I'm also teaching a course here on multimedia systems and applications, and this is the website for that in case you want to know more detailed information about how the multimedia coding and multimedia systems can be evaluated, or how the evolution has happened, and the various multimedia applications that are there already existing and are expected to come up. So thank you very much, and I now welcome the questions.
Thank you, Professor, for this enlightening talk. And we can take few questions and then we can close the session.
Maybe I'll ask a question. This is Rajesh here. My question is related to the coding standard that you mentioned, and then you highlighted the use of pictures, intra-coded and then predictive. Did you also mention the bidirectional coded pictures in your description? I missed that particular part.
So actually, because of the shortage of time, I didn't go into the details of how from Asia 261 to the later standards, instead of just I and the P frame, the B frames are also there. So I did not touch upon that aspect just because of the shortage of time.
Because of shortage of time. Okay.
Yes, yes.
Now, the reason I ask is when you bring that bidirectional coded pictures, and then you also ask about this latency related things. There is a trade-off there between some activity happening at the transmitter end, because getting the bidirectional picture requires some amount of processing. And then subsequently you send this, but that also means that in the rendering there is a delay. Of course, there is a transmission delay as well. So when these multimedia requirements are put in place, is there a discussion of these aspects also? Is that covered? And what kind of considerations are there before saying what we must have for each of those scenarios? Yeah, thank you.
Thank you for that question. So definitely when we have the bidirectional prediction, we have to wait for a future frame. And always, whenever the encoding of multimedia information is happening, it generally happens in the form of GOPs. So group of pictures are taken together and then they are encoded to get the high amount of compression efficiency. So in that way, we always have a future reference frame already available in the raw video frame GOP. Right. So what we can play with is definitely the size of the GOP. So if we reduce the size of the GOP, the buffer will be storing, let's say, instead of 30 frames, it would work with, let's say, 7 frames. Definitely the trade-off would be there in terms of the compression efficiency, but the corresponding delay in the encoded or the decoded content might be reduced. But definitely in the future standards, there are ways and means that have been introduced to speed up the process of finding the motion vectors. So for instance, like in HEVC, what is done is there is combining of these blocks such that the motion vector is not found for each block individually. But if it is identified that there is a region with a common, let's say maybe a background, which is not changing from one frame to another, Then instead of dealing with smaller blocks and individually finding their motion vectors, they combine it into a bigger block and have a common motion vector information. And also to speed up the processes, there are several other steps also followed. So instead of finding the motion vector always with respect to the previous set of frames, what they are trying to do is also by using the previously decoded or just recently encoded blocks, they repeat that motion vector information for the current block as well, if they find that there might be a match. So there are ways in which the objects can be segregated from the background. So those supports are there right from the H.264 standard. But in HEVC, further enhancements and also in BVC, further enhancements have happened such that this bidirectional prediction can be sped up. So instead of just individually dealing with each block and its motion vector, combinedly larger blocks are being used.
Okay, thank you.
Yes, thank you.
Thank you, Professor Chetna, for being a part of the seminar series and for this engaging talk.
Thank you so much.
As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will be posted on the web page. Thank you and have a great evening.